Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And so now we move to the next stage in looking at this problem, and we're looking at how GPUs can be used to create interactive visualization. And Tomas Ale.
So I'd like to talk a little bit about how GPUs can be used to visualize large data sets, because there are some unique problems that pop up when you start looking at data sets that are this big. So as we've seen a lot, we're getting better and better at storing and processing all of this data using all these new approaches like distributed databases and clouds and grids and supercomputers. And for most of these, we do find that the I/O needs to be about as fast as the computation. And in some cases, it needs to be a lot faster for databases when you need to sort the data and all that. But all the same, this doesn't work for visualization, because even for sorts, it's acceptable to have, minutes to sort your entire data set or to read your entire data set. But for visualization, you need to reread all of the data every single frame, or you need to have it all in memory all the time, because you need to constantly be processing it. That would be 10 times a second. And even rendering that much data would be prohibitive cost-wise, because to render a terabyte of data, you'd probably need about 5 or 10 graphics cards, so you can forget a petabyte. Then, of course, you could do pre-rendered movies, which is what most people do today, but they're difficult to set up, and then you often need to go back and try it again, change some parameters. And if it takes 3 days to render a movie like that, then you'll find, that it'll be months before you actually have something that's usable. So it's a pretty poor way of doing actual science and research. So, and one important application of visualizations are simulations, which are, as storage systems and processing systems get larger, simulations grow with them. So simulations are always going to be pushing the bounds of what's possible and what you can store. So this is the one that I worked on. This is the Aquarius Simulations done by Volker Springel's group at the Max Planck Institute in Munich. And there are a series of n-body dark matter simulations. What that means is that it's just particle simulations of what we think dark matter would be like, and they run from the early universe and around the galaxy. So the point is that there are 5 different resolutions, ranging from 25 gigabytes to 20 terabytes for the entire data set. And so the 25 gigabyte one is still pretty manageable, but once you get up to 20 terabytes, there are very few systems existing today that could render something of that size. And so each version has point data in these different time slices, and then you can render movies from them, but it does take weeks, unfortunately. So when doing a visualization, it's always important to ask, why? And so asking that question, we find that some things you just can't really tell without doing visualizations. I mean, there's just all sorts of qualitative impressions that you need from the data. You need to look at it to be able to see certain things that you can't get from just numbers or even from still renderings. You need to be able to move it around. You need to be able to look at it, interact with it. Another thing that's just very easy to see is just to make sure that your simulation isn't producing garbage, or to find the accuracy of all sorts of post-processing that you do on it, which I'll give an example of in a second. Some other things are, if you want to actually identify things, then what that requires is you have to look through the data. And one of the best ways of looking through lots of data really fast is using your eyes by looking at it. I mean, some of these things would actually be pretty difficult to find algorithmically, whereas if you just take a visualization and look at the data, then you can find them pretty quickly. And of course, lastly, is public outreach, which is obvious but is also important. So this is an example of what the data actually looks like. This is a still snapshot, and you can see the particles are actually much smaller. Each of these glowing blobs is a gravitationally bound group of particles called a subhalo. And one of the other important things of a visualization is that you can look at the entire data set all at once, and then you can zoom in and look at a little part of it, or you can highlight some important features like this, for example. This is 2 colliding bodies, and one of them has been highlighted. You can see the individual particles there. And so things like this are why visualizations are important. So how to do it is to do hierarchical rendering. And so the idea is that you realize that you don't need to render all of the data to get something that looks like all of the data. Because there's so much data that you would just end up filling the screen 1,000 times over anyway, so there's really no point. So what you do is you show the same information, but you render a lot less data. You load a lot less data from disk, and you render a lot less. And so you pre-generate, you pre-compute different levels of detail for the entire data set, and then you load different parts from different levels as you need to based on where you are and what you're looking at. And then you can put the levels of detail on a fast storage system, and then everything runs really smoothly as you move around. And so the faster the storage system, the faster it responds as you move around the visualization, and then you give it a nice rendering front-end program, and everything works. And the example I usually give is Google Maps, but in this case, I think Microsoft Maps would be more appropriate. So here's just the basic idea behind the structure that I chose to organize the data. It's just a simple spatial octree. There's not that much special about it. And then every node in the octree has associated data. And the data is just all of the information contained within that volume, but simplified to endpoints. In my case, n is 16,000. So basically what you get are these megabyte-sized chunks of information which represent data, the original data, at different resolutions and at different locations in the tree, or in the entire data set. And it's organized this way on disk, which is the important part, because then you don't have to scan through the entire data set to pick and choose certain parts of it that you want to look at. So the choosing process is just like this. Basically, the question becomes what resolution you want to load in from what different locations, which is what the octree allows you to do. And so the general idea is something that's close to you, you load in high detail, and something that's far away, you load in low detail. And if you use the on-screen size of the blocks to choose what you want to load, then you can actually show that you get something that's visually equivalent to rendering the entire data set. And so as a result of this, if you have a 20 terabyte point simulation, then actually by loading maybe 100 megabytes or 500 megabytes of data, you can render something that's visually equivalent from that point of view to the entire data set, which is really important because if you have a system underneath it that can stream you the relevant information as you move around, then as far as the user is concerned, they're looking at a rendering of the entire data set. And then the other benefit is that this automatically scales to the different kinds of hardware that you use, because since you have different levels of detail, if you're running on something that's sharing 50 graphics cards between multiple users, then it can automatically scale back the simulation or the level of detail as more users start rendering. And you can, all these things come automatically by just adjusting the level of details that you load. And of course, you can spread out what you load through time as well. One of the important things about this data is that it also has a temporal component. And so if you spread that out, then you can actually smoothly animate the data in real time as you're visualizing it, which is something that is not commonly found with such large data sets. So here's an example of the selective loading. So this is just to give you an example. You see that the blocks closer to the center are much smaller, which means that the data there is loaded in much higher resolution. And then as you get farther away, then they become larger. And so since each block contains 16,000 points, the larger blocks represent lower resolution data. And then you just put a rendering front end on it, which is, of course, the fun part, because GPUs are really, really cool. They're amazingly fast, and there's been a lot of work in the past few years on GPUs. And here I'm going back to using them just for plain old rendering. But the fact remains that they still can do a whole lot of computation, even in the rendering pipeline, which means that if you write a program like this, you're not just restricted to rendering. You can actually still do processing in the, as you're displaying all the data that you have. So there's the actual rendering algorithm. It's pretty straightforward. You just integrate the line of sight. It's basically just a ray traced integral, and then you have color, which roughly represents the temperature of the particles in that region, just so you have an idea of what you're looking at. But for some of the special features that the visualization has, like what you saw earlier, you can select specific features. There's actually quite a bit of computation. So one of the things you can do is you can select these subhalos, substructures, which just takes a list of, say, 1 million points, puts it on the graphics card, and then for every point that it renders from then on, every single time it renders a point, each point has a unique ID, it checks the rendered points ID against the list of the entire 1 million points to see whether it's part of it. And so that's how you can select certain points. And so the benefit of that is you can select points for the lifetime of the simulation. You can rewind the simulation all the way to the beginning to see where those points came from, or move it all the way to the end. But I mean, what I find amazing is that a graphics card has the processing capability to do a binary search through a list of 1 million entries 10 times, so 100 million times a second, give or take. And so this just has, you know, a ton of potential for all sorts of different things that you could do. So this is what the system is right now for me. It just runs on my desktop computer with 4 gigabytes of RAM and just a simple one single graphics card and just 2 disks. So 1 terabyte of data is the data set that I work with primarily, which is the medium resolution out of all the simulations. And that's just striped across 2 750 gigabyte hard disks. So, you know, you can imagine if you were to hook this up to something faster storage system, I mean, it would perform much better. But so I didn't quite reach 1 billion. The data that I'm working with only has 150 million points, unfortunately. But in theory, it should work with 1 billion because it hardly ever loads or renders all of the data. So what that means is that, you know, it could very easily work with 1 billion because it would only load the lowest resolution when you're zoomed all the way in. So I have some movies. These are just some rendered movies. This is the first one. This is just going from the start and going all the way through the entire thing. You're just watching basically the time evolution of the dark matter in our galactic neighborhood. Now, since I can't show it live, I obviously had to render some movies from the program. So this isn't actually real time or anything, but this is what it looks like if you were to just view the visualization yourself in real time. This is what you would see, and then you could just be able to pause the movie here and then fly around, zoom around, select different objects. And so that's what that was. And so here, what we have is a zoomed-in view. And so this is much more scientifically interesting. So we're watching a bunch of objects interacting, and then what I'm going to do in a second is click on one of the objects like that, and then the program actually just loads in the information about what points are selected based on what object I clicked on, and then those points remain selected after I click on them. And then you can watch the objects collide, and you see the dark matter stream forming when the 2 objects collide. And so something like this, the ability to just select objects at will, would actually be very scientifically important and useful. And so that's sort of the idea and the motivation behind this, is the ability to look around, find things, look at them more closely, watch them as they, you know, evolve through time, watch them as they change. And then here's the final one, and this is just showing the full terabyte data set being animated. And so you're zoomed in all the way on one little piece, and you see that that one little piece is in very high detail. And you see some flickering there. That's just because it's not loading in the entire thing, so it flickers a little bit as it changes between time steps. But then you can zoom all the way out, and you see this one has a lot more data than the previous one. So this is the 1 terabyte data set. And then you can zoom in all the way on the other side of the simulation. which this wasn't loaded. This part wasn't loaded previously when we were over there. This was just loaded dynamically as we moved the camera from one side to the other. And it renders that too. And so, of course, there's a lot of potential here for extending this to, move the storage to larger, more powerful systems, of course. You could do distributed rendering, which, just throw 100 graphics cards all rendering at the same time. Then you could either have more users or you could just render more data. And remote rendering, of course, is one of the really important ones because not everybody has computers with fancy graphics cards. So even if you do send the data to desktop computers, remote rendering is probably the most useful way to get it out to the public. And then, of course, there's other data sets and other data types. So meshes have the same kind of progressive level of detailing. You can do the same thing with meshes. You can do the same thing with volume data or medical imagery. So this is just an example of what is possible with all the different data types. Thank you.
We have time for questions. So perhaps you could tell us what your next steps will be.
Well, I suppose my next steps will probably be to graduate from college. And in the meantime, hopefully I'll have a little more time to work on this maybe this coming summer. But until then, I'm not really sure if I'll have the time to do a whole lot with this. Graduation is my first priority at the moment, I'd say.
And a very good one.
Yeah.
Thank you, Tomas.
Thank you.
Oh, another question.
Okay. So I think I know the answer, but I think it's an interesting question. So I know that at some point you were trying to use SQL Server to actually solve the problem. So can you tell us why you move out of that?
Oh, yes.
Yeah.
Yes, of course. So she was asking, she had heard that at some point I tried to use SQL Server in the process of doing all this. And so actually most of what the time went into was not the rendering program itself, but actually generating the different levels of details. As I found out, manipulating terabytes of data is much more difficult than one would think. And so my first attempt was to use SQL Server, but unfortunately the systems that they had at the Max Planck Institute weren't really capable of handling that much data. And so the easiest way to do it was just to write my own code on just one large disk array and just have it process it there. On the other hand, a database would be perfectly suited to this process of retrieving the data that you want because that's what they're good at. So that would, I think, be a much more useful application of a database in this case.
Thank you again.